I welcome you all in this course on mechatronics. In this lecture, we are going to talk about electrical actuation systems further. Okay, so, I have named it as electrical actuation system part 2, because as I told you in my earlier lecture that electrical actuators are one of the important component of a mechatronic system. That is why I am covering it up in 2 lectures, because these actuators are easy to control. Okay. So, in my lecture on the part 1, we have seen the relays, solenoid, and the DC motors we have seen. Okay, that is permanent magnet type as well as field winding. We have seen the series, shunt wound, and the compound wound motors, their characteristic. Okay. So, all those things we have seen. We will be further taking up some of the electrical actuators over here. Okay. So, let us begin with brushless permanent magnet DC motor. So, the simple DC motor, as I told you that we use brushes basically to reverse the direction of current in the armature conductor. Okay. And these brushes actually because of wear and tear, these brushes has to be periodically changed. So, there is a commutator problem in case of simple DC motor. Okay. So, people thought about a motor which is brushless permanent magnet DC motor, and now in this case of permanent brushless permanent DC motor, permanent magnet DC motor, we have, there are sequence of stator coils. Basically you can see A, B, C, D, say this sequence, and then you have A, B, C, D. So, these are the sequence of stator coils, and there is a permanent magnet rotor basically. Okay. And current carrying conductor, you see the current carrying conductor in a magnetic field experiences a force basically. Okay. So, here the current is carried by stator, okay, conductor in the stator, and it is there in a magnetic field. Okay. So, it experiences a force, and from Newton's third law, the magnet will also experience an opposite and equal force, and this is the basic principle of the brushless DC motor. So, in case of brushless DC motor, basically the permanent magnet rotor rotates because of the reactive forces which are coming from the stator side. So, to switch these coils in a sequence, the switching circuits are used, and this is provided by output from 3 sensors operating through a circuit to give appropriate base current, and Hall sensors are generally used to sense the position of rotor and initiate the switching by the transistors. Okay. And Hall sensors are positions around the stator. That schematic I have not included over here. You can see some of the standard textbook, then you can see the switching with the help of transistors. Next motor which I would like to take, these are the AC motors, and these AC motors are classified as a single phase motor and the polyphase motor. Single phase motors are used for the low power, whereas the polyphase motor are used for the high power. Okay. And these motor, whether it is a single phase or polyphase, they could be further classified as the induction motor or the synchronous motor based on the principle they use for the operation. Okay. These AC motors are cheaper compared to DC motor, but their speed control is difficult. Okay. So, you will find that most of the motors which are used in the general smaller applications, they are the DC motors because it is easy to control them. Okay. The speed control of AC motor is based on the provision of variable frequency supply basically. Okay. Since the motor speed is determined by the frequency of the power supply. So, now let us look at the basic induction motor first, then we will be looking at the synchronous motor. So, let us look at the induction motor first. Okay. So, in a brush DC motor, you see electric power is conducted to the armature through brushes and the commutators, we have seen in the previous lecture. Okay. And hence these DC motors are also known as the conduction motors, okay, because the armature conductor carry the current through them. So, they are called as the conduction motor, whereas in a AC motor actually the rotor receives power by induction in contrast to the DC motor which receive power by the conduction. Okay. So, in AC motor the rotor receives power by the induction, okay, and this induction in AC motor is very similar to the secondary side of a two winding transformer which receives power from the primary. So, I hope you must have studied the transformer where you have the primary side, okay, and we have the secondary side. So, something like this it is there. Okay. So, here in case of induction motor the operation is AC motor is similar to the secondary side of a two winding transformer. In fact, an induction motor can be treated as a transformer, okay, whose primary winding is stationary, but the secondary is free to rotate. Okay. This way we can carry out the treatment of it. Okay. And the major difference is the air gap between the rotor and the stator through which the flux passes. Now, let us see the single phase squirrel cage induction motor. Okay. So, here you have a rotor over here, okay, and there are the rotor conductors and you have the poles basically which form the stator actually, okay, or stator forms the pole. So, the squirrel cage induction motor consists of a squirrel cage rotor made of copper or aluminum bar and that fits into the slots over here as you can see, okay, in end rings to form complete electrical circuit, okay, and there is no external connection to the rotor here. You see, I am repeating this again, there is no external connection to the rotor because here we are talking about the AC motor. These conductors are not supplied with the external power supply, okay, and the stator consists of set of windings over here as I said, okay, and when the alternating current passes through the stator winding and alternating magnetic field is produced, and because of this alternating magnetic field electromagnetic induction takes place in the rotor and an EMF is induced in the conductor of the rotor and current flows through the rotor. Okay. Thus, we have the case of current carrying conductor placed in a magnetic field. Okay. So, this is why how it is done. Okay. So, now with this induction principle, what happens, you see, initially when the rotor is stationary, okay, the forces on the current carrying conductor of the rotor in the magnetic field of the stator are such that there is no resultant torque. Okay. So, initially your rotor is not rotating. So, that is why this motor is not self starting, you need something to start an induction motor. Okay. So, devices are used with the this motor. Okay. Now, the rotor rotates at a speed determined by the frequency of the alternating current which is being applied to the stator. Next, let us look at the synchronous motor. Okay. Now, they have a stator similar to the induction motor, okay, but the rotor which is a permanent magnet. Okay. In this case, the rotor is a permanent magnet, whereas in case of induction motor, the rotor was simple conductors were there. But in case of synchronous motor, we have a permanent magnet rotor. The magnetic field produced by the stator rotates, and so the magnet rotates with it. So, here as you can see that these are the stator and this is the rotor. Now, when one pair of pole per phase of the supply, with one pair of poles per phase of supply, the magnetic field rotates through 360 degree in one cycle of supply, and so the frequency of rotation with this arrangement is same as the frequency of the supply. Okay. And synchronous motors are used when we need a precise speed control, okay, when a precise speed is required, and they are not self starting, and some system has to be employed to start them. Next, let us look at the stepper motor. As the name indicates, okay, these motors moves in steps. Okay. So, they are a special type of DC motors, okay, and it can rotate in both direction and move in a very precise angular increments. Okay. Sustain a holding torque at 0 speed and be controlled with the digital circuits. It moves in very accurate angular increments known as steps in response to digital pulses sent through an electrical drive circuit. Okay. The number and the rate of these pulses actually control the position and speed of the motor shaft. Generally, step motors are manufactured with step per revolution such as say 12, 24, 72, 144, 180 and 220, and this results in say shaft angle of say 30 degree, that is 360 divided by 12. So, this is your 30 degree. So, 30 degree, 15 degree corresponding to this, 72, 5 degree corresponding to 72 steps and so on. Stepper motors are either bipolar, that is they require two power sources, or switching or a switchable polarity power source, or they are unipolar requiring only one power source. They are powered by DC sources because basically they are DC motors, okay, and require digital circuitry to produce the coil energizing sequence for the motor rotation. Okay. As we will be I will be explaining to you how we get the different steps. Okay. Okay. And feedback is not always required for control, but why we do not require feedback? Because here we make the motor rotates in a step, and many times we know that how much steps it has to rotate, and so how many pulses has to be given. Okay. But if you have provision of position sensing, then it can ensure the accuracy, okay. And they are used in low power position control application, usually less than say 1 HP or say 746 watt. They are classified as permanent magnet or the variable reluctance stepper motor. Okay. In case of a permanent magnet stepper motor, the stator consists of wound poles, as you can see over here, these are the wound poles, okay, and the rotor poles are the permanent magnet here. Okay. So, this is your rotor. And when we excite stator windings combination, the rotor moves and holds in the different position. Okay. So, as we supply the power to the different windings, okay, this motor rotor rotates. And in the variable reluctance type stepper motor, the working principle is that there is a ferromagnetic rotor rather than the permanent magnet motor. So, this is your ferromagnetic rotor is there, okay, and the motion and holding results from attraction of stator and rotor poles to position with minimum magnetic reluctance, okay, that allow for the maximum magnetic flux. These stepper motor can be specified by say phase, that is the number of independent winding in the stator, step angles, that is the rotor rotation for one switching change for the stator coil, and the holding torque, that is the maximum torque that can be applied to a powered motor without moving it from its rest position and reversing spindle rotation. Let us see the working principle of permanent magnet stepper motor. Okay. The motor shown has the 4 poles, stator with 4 poles. So, you can see 1, 2, 3 and 4, these are the 4 poles, and here by changing the direction of current we can change these poles basically. Okay. So, each pole is wound with field winding, the coil on opposite pair of poles being in the series, and current is supplied from a DC source to the winding through the switches, and the rotor is a permanent magnet, and thus when a pair of stator poles has a current switched on it, the rotor will move to line up with it. Let me explain this further over here. So, as we can see this figure, so suppose in this one this is the direction of current over here. So, say this pole is north, this pole is south, and this is my permanent magnet rotor over here, and in this one this is the direction of current. So, this is north and this is south, south pole. Okay. Now, what happens if I change this direction of current over here. So, this is the configuration, okay, that is this becomes south and this becomes north, okay. Then what will happen, this south and this north will try to align, and so the rotor will be turning like this, okay, and it will be moving to this position. And in the next turn what we can do, that we change the polarity of say these poles by changing the direction of current over here. So, this becomes north and this becomes south. So, this was the earlier condition, okay, and so this will be attracted basically over here, this is already south. So, this north will be attracted over here, and there is going to be a full 90-degree rotation over here, okay. And then further if again we change the polarity like this, this becomes north and this becomes south, okay. This was the earlier one, Okay. So, again we see that this turns further from here. Okay. This been converting into the south, this will be turning over here and it will be trying to align it. Okay. So, thus the rotor rotates here in one step. You can see that there is a rotation of 90 degree. Now, let us see the variable reluctance stepper motor. So, as I said, in case of variable reluctance stepper motor, here in place of permanent magnet, we have the rotor is made of the soft steel and it is cylindrical, say with 4 poles. Okay. There are 4 poles and less number of poles than in the stator. So, here you can see in the stator has 1, 2, 3, 4, 5, 6 poles and the rotor has got say 4 poles. Okay. Now, when an opposite pair of winding has current switched to them, okay, the field is produced with lines of force which pass from the stator pole through the nearest set of poles on the rotor. So, it is basically something like your stretching of the thread. Okay. So, the lines of force can be considered to be rather like elastic thread, as I said, and always trying to shorten themselves, and this way the rotor will move until the rotor and stator poles line up basically. Okay. So, that way we get the rotation of the rotor. Okay. And this is termed the position of the minimum reluctance, and that is where the shortest path is there, and this stepper motor generally give step angle of 7.5 degree or 15 degree. Now, there are hybrid stepper motor which are combination of the permanent magnet and the variable reluctance basically. Okay. So, you can see here. So, there are teeth in the cap basically to provide the variable reluctances. Okay. So, basically the same principle used as the variable reluctance over here, and this is you can see the exploded view here. So, basically this is the rotor. Okay. So, you can see that the end caps over here and there are teeth over there. So, this is the hybrid stepper motor, and this combine the features of both variable reluctance and the permanent magnet motor. Okay. So, the rotor sets itself in the minimum reluctance position in response to the pair of stator coil being energized, and this is used in your computer hard disk drive. Now, let us look at the dynamic response of a single step of the stepper motor. So, if I plot say the rotation versus time. So, say if this is the step size, naturally my motor will not directly jump into this step, rather it follows this path, okay, and it tries to settle after some time on the step size. If I add some damping to it, okay, then basically these oscillations can be reduced, and so with aided damping this is the behavior which can be obtained. Now, these stepper motor torque speed curve, if we look at basically, okay, so there are two modes, one is called the locked step mode and other is called the slewing mode. Okay. In locked step mode, the rotor decelerates, okay, decelerates and may even come to the rest between each steps. Okay. And within this region the motor can be instantly stopped or reversed without losing step integrity. Okay. And in the slewing mode, the speed is too fast to allow the instantaneous starting, stopping and reversing, because you see that this is obtained at a greater speed range. This is how this commercially available stepper motor looks like. One can usually identify the stepper motor with the so many wires over here. Okay. So, these wires usually have a certain current coding color coding being done. Okay. So, this figure shows unipolar stepper motor field coil scheme with external power transistors, as you can see over here. Okay. That must be switched on and off to produce a controlled sequence of stator polarities to cause the rotation, and this schematic corresponds to the 6 wire basically connected to the motor. So, you can see that we have 1, 2, 3, 4, 5, 6. Okay. So, yellow, red, orange, black, green and brown. So, this is the color coding done over here. Usually the second and fifth they are usually joined together internally. Okay. So, the second and fifth wires are usually connected externally as shown, and manufacturers sometimes connect them inside the motor also, in which case the motor only has the 5 external wires. The wires are usually color coded by the manufacturer to help the user make a correspondence to the schematic. Okay. And figure include common color schemes used for say 6 wire unipolar stepper motor. Yellow is coil 1, red is 1 or 2 common, orange is coil 2, black is coil 3, green 3 or 4 common and brown is coil 4. Okay. So, the most commercially available stepper motor have 200 steps per revolution in the full step mode, and are sometimes referred as 1.8 degree stepper, that is 360 divided by 200. There is a drive circuit for these stepper motor actually, and this drive circuit comes in a single monolithic IC. Okay. So, there are various brands of these drive circuits. For example, E-Lab has got ED 1200, Synetics has got SAA 1027, and Alargo Microsystem has got UCN 5804B. Okay. And these have circuits have actually the 7414 ischemic trigger, this one. Okay. Buffer to provide sharp square wave signal, that is, and 74191 up down counter, this one which provide to least significant output bit B0 and B1, and 7486 exclusive OR gates are there. Okay. So, some of these things I will be taking up in my coming lectures. Now, let us after seeing these many motors, various types of motors we have seen. So, in this lecture we have seen the AC motors and we have seen the stepper motors. Okay. So, the question is how do we select a motor? Okay. So, when we are selecting a motor for a specific mechatronic application, the designer must consider many factors. Okay. What are these factors? What speed range I am going to use for the motor? Okay. What is the torque speed variation or torque speed characteristic? My requirement is that whether I want a motor which should be reversible, and what should be the operating duty cycle for the motor, what is the starting torque for the motor, and what is the power required for the motor. Now, the torque speed curve provides answer to many questions about a motor's performance. Okay. And most of the manufacturer actually provide this torque speed characteristic with the motor, okay, and the torque speed curve displays the torque the motor can deliver at different speeds at a rated voltage. Okay. So, for example, here the motor and torque and motor speed, say this limit provides the commutation limit, driver torque speed is here, and motor continuous operation boundary, this curves provide that. Then there are a list of questions that designer must consider when selecting and sizing a motor in consultation with a motor manufacturer. Okay, what could be these questions? Will the motor start and accelerate fast enough? What is the maximum speed the motor can produce? What is the operating duty cycle? How much power does the load require? What power source is available, and what is the load inertia which is permissible? Is the load be driven at a constant speed? Is accurate position or speed control is required? Is the transmission or gearbox is required? Why transmission or gearbox may be needed? Many times we have the high speed motors are available, but our speed requirement may be low or torque requirement may be high. So, we need the gearbox, and the transmission system such as say gears or belt you may require if your actuator is not at that particular position. For example, in case of robots, okay, many times your actuator is not at the robot joint, it is at far off place. So, you require the power to be transmitted from distance place to that particular joint. So, you require a transmission system. Okay. Next question could be, is the motor torque speed curve well matched with the load speed curve? Okay. And for a given motor torque speed curve and load line, what will be the operating speed? Is it necessary to reverse the motor? Are there any size and weight restrictions? Many times we may have the size and weight restrictions. Okay. You see in robotic application, because when we are talking about manipulator arm, okay, the arms has to carry the motor weight. So, naturally at one way the motor weight is going to be added to the arm weight. Okay. So, we have a restriction, the weight restriction. We may also have the size restriction depending on the space available. Okay. So, these are the some of the questions which the designer of mechatronic system has to ask to the motor supplier. Now, for a given motor torque speed curve and a well defined load line, okay, the system settles at a fixed speed operating point. Okay. So, if I talk about the torque speed curve like this, so this is say the motor torque speed curve, okay, and this is my load line. Okay. That is how my load varies with the operating load varies with the speed. So, now we can see that there is a intersection point, and this intersection point is what we call it as a operating point. Okay. And this operating point, as we will see, is self regulating. How it is self regulating? Let us see that. Okay. So, at lower speed the motor torque exceeds the load requirement. Okay. So, motor torque exceeds the load torque, and so what will happen? The system will accelerate towards the operating point. Okay. But at higher speed, if we are talking about at higher speed, the load torque exceeds the torque supplied by the motor. Okay. So, that reduces the speeds towards the operating point. Okay. So, this operating point is actually self regulating. Okay. So, the operating speed can be actively changed by adjusting the voltage supplied to the motor, which in turn changes the torque speed characteristic. So, if you want further read, please refer to again the very good resource available in Bolton and Intelligent Mechatronic System, that is our book, and the one Introduction to Mechatronics by Alciator and Histand. Thank you very much.